Hello and welcome to the lecture on 6.5. Today we're going to talk about the law of sines. The next two sections we talk about how we're going to use trig functions to solve some oblique triangles. Oblique triangles are simply not right triangles. Let's derive the law of sines really quickly here. Suppose we have this triangle here. Now we're going to need to know the height, but we'll get there in a second. Call this A, means this is angle A because sides and angles are always opposite each other. Call this side C, this is angle C, this is side B, this is angle B. And our height here is h. Now remember, in a right triangle, sine of an angle, call it sine of angle C, is going to be the opposite over the hypotenuse. Now we have a right triangle here, so sine of angle C will be the opposite h divided by b. Okay. Now if we multiply b over, we would have h is equal to b times sine of c. Wait a minute. What if we also looked at this right triangle? Because this also creates a right triangle. And we look at h on this side. So we can also say that sine of angle B is equal to h divided by its hypotenuse, which is c. Multiply this over, and we have h is also equal to c times sine of angle B. Just like this. So now h is the same length. So we can say b sine of c is equal to c sine of b. And if we divide both sides by c and b, we would have sine of c, sine of angle c that is, divided by c is equal to sine of angle b divided by side b. Now this is the basis of the law of sines. And if we rotate our triangle, we can get the other equalities, but I'm going to stop here with the derivation and move right into the law of sines. In a triangle ABC, sine of angle A divided by side A is equal to sine of angle B divided by side B is equal to sine of angle C divided by side C. Now this is usually pretty easy to remember. Most of the time, people can remember sine of A divided by A, sine of B divided by B, sine of C divided by C. The important part in this is the setup. Remember that our triangle, the angle with the same letter, is opposite the side. So side A is here, opposite this side is this angle, which means that this is angle A. Similarly, we have an angle B here, opposite this angle is this side, which is side B. We have angle C, opposite angle C is side C. That's how we have to set it up in order to use the law of sines correctly. In order to solve an oblique triangle, we need 3 pieces of information. And there are 4 different cases that we need to run through. 2 of them deal with the law of sines, 2 of them deal with the law of cosines, which will be next section, 6.6. Let's start with case 1. And we'll go over exactly what we know about the triangles. So case 1 is one side and 2 angles are known. So if we had a triangle, say that this is our triangle, and we knew this side, and then we knew this angle and this angle, we would use case 1 when trying to solve the triangle. It doesn't matter which 2 angles we know, as long as we know 2 angles and one side, we'll always use case 1 of law of sines. It's the easiest way to solve the triangle. Now case 2, this one's a little bit trickier. 2 sides and an angle opposite a known side are known. Now let's draw a triangle here. Suppose that we have this. Now, if we know this side and this side, in order to fall into case 2, we would either need to know this angle or this angle, because we need to know an angle opposite a known side. We know this side and this side, which means we need to either know this angle or this angle in order to use case 2. Case 2 is probably the hardest of all of the cases, and that includes the law of cosine cases. So we'll go over that one a little bit slowly. I'll leave case 3 and case 4 for the law of cosines, which will be next section. Okay. One last thing that we need to recall, In a triangle, the sum of all angles is 180 degrees. Let's get on with case 1. One side and two angles. Now, using the law of sines is usually pretty easy, again, except for case 2. Case 2 is pretty challenging. But overall, using the law of sines is pretty straightforward. Let's do an example here on how we use it. And usually your problems will say solve the triangle. And when we solve a triangle, we're looking to solve for every side and every angle. So if this is our problem, we would be given a triangle that looks like this. We know this side length is 10, this angle is 45 degrees, and say that this angle is 60 degrees. If we know these 3 pieces of information about the triangle, we have 3 more pieces of information we need to solve, namely this side, and this angle. Now this falls into case 1 because we already know 2 angles. 2 angles are known, and 1 side. So I'm going to go ahead and label my triangle next. Say we have C is equal to 10. That means that this angle is C, which is 60 degrees. We have our angle A here, which is 45 degrees, which means this is side A, and then we have an unknown angle B and an unknown side B. Okay, so how do we start this? Well, the easiest and most logical way to start this problem is to get the third angle. We can solve for A. That will be our next step, but usually solving for all of the angles is pretty straightforward when you already know 2. So again, all angles add up to 180 degrees. So we know that angle A plus angle B plus angle C is equal to 180. Now angle C is 60 degrees, angle A is 45 degrees, and we don't know what angle B is. So subtract 45, subtract 60, same thing as subtracting 105, and we get that angle B is equal to 75 degrees. Obviously not well drawn in my picture. The next 2 pieces of information are going to be side B and side A. We need to figure out what those are. So let's start with side A. We're going to use angle A because it pairs with side A, because that's what we need, and we're going to use angle C and side C. Now, why are we using angle C and side C? If we tried to use angle B and side B, we would end up with an equation with 2 unknowns. Remember, the law of sines is sine of A divided by A is equal to sine of B divided by B, which is also equal to sine of C divided by C. So if I were to plug in angle B, I would still have an unknown of side B here. So B would be unknown. Similarly, if I plugged in angle A, I have an unknown of A. Now, when we create an equation, we want a single unknown in order to isolate that unknown so that we can solve for it. So in this case, we're going to use side C and angle C here. So we have sine of A divided by A is equal to sine of C divided by C. Now notice we know both pieces of C. We know the side C is 10 and angle C is 60. And we know angle A is 45. So when we plug these in, we get that sine of 45 divided by side A is equal to sine of 60 divided by 10. All we need to do is solve for A now. Now, a lot of times students have trouble getting an unknown out of the denominator. You always want to get your unknowns into the numerator first. So multiply your A over, and then multiply by 10, and divide by sine of 60. Let's go ahead and multiply our A over. We have sine of 45 is equal to A times sine of 60 divided by 10. Multiply both sides by 10, and sine of 45 equals A sine of 60. And then divide by sine of 60. So we have 10 times sine of 45 divided by sine of 60 is equal to a. We know what sine of 45 and sine of 60 are, so we can solve this very easily. Now, sometimes you'll need to use a calculator when you don't have an angle that's on the unit circle. In this case, they're on the unit circle, so we can solve it. Sine of 45 is, of course, root 2 over 2. Sine of 60 is, of course, root 3 divided by 2. We have 10. And if you don't notice, these will cancel just by flipping and multiplying. And we'll end up with a is equal to 10 times root 2 divided by root 3. And I'm just going to write that here. 10 times root 2 divided by root 3. The last thing we need to solve for is side B. And we do the exact same thing. Now again, I'm going to use angle C and side C. Now why do I not want to use angle A and side A? Well, I don't like to use them because this will be a rounded term when you actually plug it into a calculator. Unless you want to deal with square roots, the exact value, then I think 10 and 60 is a lot easier to deal with. But a lot of times students will use a side we just found. You don't want to do that because these are exact. This, after you plug it into a calculator, will be rounded. So we do sine of B divided by side B will equal sine of C divided by side C. Now, we just plug in our values. Angle B is 75 degrees, so we have sine of 75 divided by side B, which is equal to sine of 60 divided by side C, which is 10. Cross multiply, so we have 10 sine 75 is equal to B sine 60. Now, sometimes it will help. Then just divide by sine of 60, and we have B is equal to 10 sine 75 degrees divided by a sine of 60. Now, once we plug this into a calculator, this is going to be approximately 12.722. And A is approximately 8.165. For side B, 12.722. Now we've solved for every side of our triangle and every angle of our triangle. So we know what our triangle is. We know what all of the information about our triangle is. I want you to try one on your own. Try one on the accompanying worksheet. The Dawn of Tranquility is hovering above Scarif. Two star destroyers 3 kilometers apart are firing at it at an angle of 85 degrees and 80 degrees. Solve the triangle created by the 3 ships.
We can't raise them. All rebel frequencies are blocked.
Keep trying. Engage those star destroyers and let's start probing that shield.
Yes, sir. We're going in.
So we have 1 star destroyer here. We have another star destroyer here, which is 3 kilometers away. Say that it's 3 kilometers from the center. And then we have the Dawn of Tranquility. My artsy skills not coming out very well. This is the Dawn of Tranquility here. We know that this angle is 85 degrees and this angle is 80 degrees. So you need to solve for this side, and this angle. Move on to case 2, where we know 2 sides and an angle. Now this case is called the ambiguous case. In the ambiguous case, there are 3 possibilities. You either have no solution, 1 solution, or 2 solutions. So that we have this as our known so far. Suppose that we know this angle, this side, and this side here. I'm going to come back to this side in a second. Let's say that we know this angle, this side, and this side. And we know this side, this side, this side, and this angle for all of these different triangles, okay? And triangles is a bit of a stretch sometimes. In this case here, this very first case, if this is the actual length of the side, this is the actual angle, and this is the actual length of this side, you can already see that there is actually no solution. Because if we know the length of this side, and it can't reach the third side, so suppose that this length is exactly this long, you can see that we don't actually have a triangle. We know this angle, we know this side, but this side down here can stretch as far as it needs to in order to connect to this side. But this side can't even reach this side given this angle and this side length. So in this case, this would be a no solution case, where we don't actually have any possible triangle that can connect. Now, a one solution case, there's a couple of ways to actually do it. I'm going to show you one way, and then below I'll show you another. First, let's show the right triangle. Suppose that we know this side, and it's exactly the length that we need it to be in order to barely reach this third side. Then what we have is a right triangle. So this would be a one solution case. Now there's another one solution case, and we'll draw that down here. And I'll get to that in a second. So again, suppose that we know this side, or this angle. We know this side. And we know this side. Now in this two solution case, suppose that this side is exactly this length. Suppose that this side is exactly this length. Okay? Now watch as I move this around. So if I move it over, I still have the exact same side length here, except now it shows a different angle for this angle here. This angle, because it's unknown, has two possibilities. It could be this angle, or it could be this angle, which is a little bit bigger. So we have these two different possibilities. Note that this side length is known, but this angle is not. So this length and this length are the same. Now, because we don't know what this angle is, it could be this angle, or it could be this angle. Notice that this side length didn't change. Neither did this side length, and neither did this angle. All three of the knowns have not changed, but we have two different possibilities. We have this angle here for our third angle in the triangle, or we have this angle here for our third angle in a triangle. So we have either this black triangle or this triangle with a red leg, but they both fit the given conditions. So here we actually have two solutions. And it's possible in this case. Now I'm going to show you something similar. Now another one solution case might look like this. Now you say, well, what if we swing the leg like you did here? I took this leg, I swung it around, and I reached this point here. The problem is that this leg is longer than this leg. So if I try to swing it, I swing it around, and it misses over here. So it's not possible to have a second triangle when this leg is longer than this leg, or the given knowns that we had, which would be this angle, this side, and this side. So this is still a one solution case. Now the two solution case is tricky. So we'll get to this. We'll do one of each. A no solution, one solution, and a two solution. Do an example here. Solve for all possible triangles. Now this will be the directions for the next couple of examples. We're gonna change up our triangle lengths measurements a little bit as we move through so that we can get each case. So suppose we have angle C here is 30 degrees. This side length is B and it's 10. And this side length is 7, which is C. This is angle A, side A, and angle B here. Now, let's see which case we have. It starts out exactly how you would think it would start out, where we use the law of sines. Now, because we don't know two angles, I can't solve for an angle like we could in case 1. If you have two known angles, you can solve for the third, but we have only one known angle, so we can't solve for both of them using a single equation. So, we use the law of sines, which is sine of 30, that would be angle C, divided by 7 is equal to sine of angle B divided by 10. We use angle B because we know what side B is. Now, we're trying to figure out what angle B is. So multiply 10 over. Sine of 30 is 1/2. So we have 10 times 1/2 divided by 7. So this is exactly 5 divided by 7, which is equal to sine of B. We need to figure out for what angle does sine give us 5/7. And if you remember from previous sections, we talked about all possible angles for which sine will give us 5/7. Notice that we have the equation sine of B is equal to 5/7, and not the equation sine inverse of 5/7 is equal to B. These two are different things. Remember, sine inverse has a restricted range. It can only give us certain angles. Sine, however, does not have a restricted domain, so we can have as many angles as we need. So we're looking for all possible angles between 0 and 180, such that sine gives us 5/7. Now, if we look on our unit circle, 5/7 would be right about here. So there are two positive angles for which sine gives us 5/7. That would be this angle, call this theta, and we have this angle, call this phi. So we have these two angles will still yield sine of B is equal to 5/7. So sine of phi equals 5/7 because that's the y value of this line. And sine of theta is equal to 5/7 again because the y value is the same. Notice here that 5/7 is positive. Also notice that theta and phi are both less than 180 degrees. How do I know that they're less than 180? Remember that directly across is 180 degrees. We can see that theta and phi end before 180 degrees, therefore they are less than 180. So they are both possible angles to a solution. So let's go ahead and figure out what that is in a calculator, because we need to do the inverse sine in order to find this. Now remember, the inverse sine will give you a single angle. So if we do sine inverse of 5/7, we get 45.585 degrees, roughly. Now, how do I figure out this angle, phi? Remember, sine inverse will only give you an angle between negative pi over 2 and pi over 2. That's the restricted range. So it's giving us angle theta. We need to figure out what angle phi is from angle theta. Now, I want you to notice that this is also angle theta, this distance. This distance here is the same as this distance. Notice that phi plus theta is equal to 180 degrees. So, in order to find our angle phi, we would do 180 degrees minus sine inverse of 5/7. Now, it might be the case that this angle is not possible. We'll see if that's the case in a second. So 180 degrees minus 45.585 degrees will be 134.415 degrees. Okay. Notice that this is a possible angle for a triangle because it's less than 180 degrees. Now let's draw out our two triangles. The one that I have drawn here is this triangle with the 45.585. We have angle A, angle B, this is 10, and this is 30 degrees. And this is 7. This is theta. So we would have our angle B comes out to the theta angle, which is 45.585. So we can put that here. Do that in red. So we have 45.585. Now let's draw our other triangle. Suppose our B angle instead was the phi angle, which was 134.415 degrees. And we would then have a triangle that looks like this, where B is this is still 30, this is still 10, and this is still 7. But this angle here, this angle B, is 134.415 degrees. So notice that the sides didn't change. This length is the same as 7, this length is 10, still 10, and 30, 30. The given information didn't change. The only problem is that we had two possible solutions with the given information. That's all. Now let's solve this first triangle. I'm going to finish this triangle out. How do we proceed? Well, now we have two angles. We have 30 degrees and 45.585. So we can figure out what angle A is. Angle A plus 30 plus 45.585 is going to be equal to 180 degrees. So angle A will equal 104.415 degrees. Now once we have that, we can use the law of sines to figure out side A. Now all we're missing is side A. So again, use the law of sines. Sine of 104.415 divided by side A is equal to sine of, you want to use the C side because it was given information. So sine of 30 degrees. This is unrounded. Cross multiply. 7 sine 104.415 equal to A times sine of 30. Sine of 30 is just 1/2, so you multiply the 2 over and you get 14 sine 104.415 degrees, which is equal to A. And side A comes out to approximately 13.559. This would be about 13.559. We do the exact same thing for the second triangle. Now, we just have a different angle B. So, again, angle A plus 30 plus 134.415 is going to equal 180. Now here is where we would know if we actually have a single solution or two solutions. If angle A turns out to be a negative angle, then you only have a single solution. And we'll get to that in a second. We'll do an example like that. But in this case, it doesn't. Angle A ends up being approximately 15.585 degrees. So we can write that here as 15.585. And then we use the law of sines to find side A, which again is here. So sine of 15.585 divided by side A is equal to sine of 30 divided by 7. We use information that's given. We use 30 and 7 because it's given information. It's not rounded. B is a rounded angle. So I don't want to use that. Cross multiply again. 7 sine 15.585 equal to A sine of 30. And again, sine of 30 is exactly 1/2, so we just multiply the 2 over, and we get 14 sine 15.585 is equal to A. Now, we just solve this and we get A is going to be approximately 3.761. We can write that here, 3.761. And now we've solved for all possible triangles. We could have a triangle for which angle B is 45.585 degrees, or we could have a triangle for which angle B is 134.415 degrees. Both of them are solutions with the given information: 30 degrees, side length 10 here, and side length 7 here. Okay, let's do another example. Solve for all possible triangles. And this time we have a similar triangle, but our side length is a little bit shorter. So this is still going to be 30 degrees. Still call it angle C. Still call this angle B, which is length 10. But this third side is going to be 4. Now I want you to notice that all I'm doing is changing this side of the previous triangle. Our previous triangle had a 7. I'm making it a 4 now. But the other two pieces of information are the same. B is 10, C is 30. Just adjusting this side, we can tell whether we get a 2-solution case, a 1-solution case, or a no-solution case. So this is still angle A, still have side A and angle B here. So we're still looking for angle B, side A, and angle A. And we start the same way. Because we don't know 2 angles, we only know 1 angle, we can't solve for a third angle, so this falls to case 2. So we're going to use law of sines in order to figure out angle B. So we get sine of B divided by 10 is equal to sine of 30 divided by 4. Multiply the 10 over. Sine of B is equal to 10 divided by 4 times sine of 30. So we have 5 over 2 times sine of 30. And I say 5 over 2 because I reduced. We would have a 10 divided by 4, but they are both divisible by 2. So we have 5 over 2. Now sine of 30 is exactly 1/2. So we have 5 over 4 is equal to sine of B. Now, what we're looking for is for what angle B, sine gives us 5/4. And think about that for a second before you go looking for it, or before you plug it into a calculator. Think about the value of 5/4 and the range of sine. Remember, sine can only give a number between -1 and 1, but 5/4 is 1.25. It's outside the range of sine. Therefore, this is actually impossible. This is never equal. What that means in our picture is that we have a case that looks like this, where this leg doesn't exactly connect. Remember that I told you that we shrunk this leg from the previous example. We had a 7 before, now we have a 4. I shrunk it too far, so now it gives us a no solution case. We have no solution in this case. Let's do another example. Solve for all possible triangles. And our triangle is going to be very similar again, where we have something that looks like this. Again, an angle of 30 degrees. Call this angle C. This is side B is 10. Angle A, side A, angle B, which I don't know, and I know side C in this case is 11. I want you to notice something really quickly. Notice that C is larger than B. That's going to come into play in a second. I'll explain why in a sec. So, again, first things first, we would like to find all the angles, but we can't. We only know one angle. I can't solve for 2 different angles using a single equation. So, we resort to law of sines immediately. Sine of angle B over 10 is going to equal sine of angle C, which is 30 degrees, divided by 11. Multiply the 10 over, and we have sine of B is equal to 10 divided by 11 times sine of 30. Now again, sine of 30 is exactly 1/2, so this becomes 10 over 22. We can reduce this to be 5 over 11. So now, just like when we had the 2 solution case, we are looking for all possible angles B for which sine gives us 5/11. Okay? Not just the inverse sine. So it is, again, possible that we have a case that looks like this, and then another case where it looks like this. This is a possibility. It won't be in this case. It won't be the case, but it is a possibility that we have to account for. So again, we go with our angle theta and phi. In the unit circle, remember, we called the first one angle theta and the second one angle phi. So let's say that B is equal to theta. Now, theta is just going to be the sine inverse. It's our first angle. So sine inverse of 5/11. Sine inverse of 5/11 is 152 degrees. Is that right? That's not right. Sine inverse of 5/11 is 27.036. So we end up with 27.036 degrees. And then we have to subtract this from 180 to get our phi. So phi is equal to 180 degrees minus theta. Our first possibility will be when B is equal to 27.036 degrees. Our second possibility is when B is equal to phi, which is 180 minus 27.036 degrees. And again, that's because we can play with our angles. This measurement here is the same thing as theta. And since it completes 180 degrees with phi, we know that phi plus theta is going to equal 180. And this ends up being 152.964 degrees. Okay. So let's go ahead and continue with this triangle here. So let's redraw it. We have our 30-degree angle. B is 10, C is 11, and then we have this angle, which is 27.036 degrees. Now we're looking for angle A and side A. So angle A, because we know that all three angles add up to 180 degrees, angle A will be 180 minus 27.036 minus 30. That should give us 122.964 degrees. We know what angle A is. That's 122.964 degrees. And then we use the law of sines. And that's it for this one. So sine of angle A, which is 122.964, divided by side A is equal to sine. Again, we use the C's because they're given. So sine of 30 divided by 11. Cross multiply. And we have 11 times sine of 122.964 is equal to A times sine of 30. And again, sine of 30 is equal to 1/2, so we just multiply the 2 over. So we have 22. 2 times 11 is 22, so we have 22 times sine of 122.964 is equal to A. Doing that in a calculator, and we get that A is equal to 18.644. So 18.644. Okay. Now we need to do the second triangle. Remember, if it exists, it might not. In this case, it actually will not. And we'll be able to see that right away. So this triangle would actually be the one where angle B is a very large angle. It's obtuse. So we'd have side A, and then angle B would have to look something like this. And B, remember, is 152.964. We have this side is 10 still, and this side angle is 30, and this side is 11. Okay, notice that we have an angle 30 and an angle 152, and we need to figure out what this angle A is. Remember, angle A will equal 180 minus 30 minus 152.964. Now remember what I told you before. If the second triangle doesn't exist, when you look for your angle A, the third angle, the last angle that you're missing, you'll get a negative angle. And that is exactly what happens here. A ends up being negative 2.064. This is impossible. How do you have a negative angle in a triangle? That doesn't make any sense. So we actually don't have a second triangle. And that comes from here. Remember what I said here, if this leg is longer than this leg, when I try to swing it around, it misses this line until it gives you a negative angle, essentially. There is no actual possible second triangle. Okay, go ahead and try one on the accompanying worksheet. Solve for all possible triangles. And we have our triangle looks like this. This is 45 degrees. This is 6, and this is 5. Okay, be careful. Don't forget to look for a second triangle. All right, that's going to be it for today. I will see you all in the next lecture.